Okay, so for this circuit, we have to find the transfer function and identify the type of filter the circuit represents. So here, let's so pretty much to get the transfer function, we have to get VO of t over VI of t. So we have to solve for these t values. Okay. Well, let me make this problem a little bit. There we go. Okay. So let's first thing we can do is get the impedance values for everything. So the impedance value for this is just R. For the inductor, it's just JWL, and this is just R2. So let's combine these two first. So it'll be the following. So it'll be 1 over JWL plus 1 over R2, all to the power of minus 1. Okay. And for this, we can like change it up a bit. So what first thing we can do is times this side top and bottom by JWL and times this side top and bottom by R2. Okay, and then this is just JWL plus R2 all over JWL R2 all to the power of minus 1, and that's just JWL R2 all over JWL plus R2. So we can replace that with pretty much this. So this is equal to JWL R2 all over JWL plus R2. And recall the impedance of this is just R1. So to get VI of t, it'll be your impedance equivalent, JWL R2 plus JWL plus R2 plus R1 times the current passing through, which will just be I. Now, your VO of t is actually pretty easy to solve for, because notice here, this is grounded, so this is 0 volt. So that means here it should be VO of t, and that means at this region it should also be VO of t, because this is just one closed node. So that means at this load here it would be VO of t, as this is also the ground. So that means if you were to combine these two, the load here would still be VO of t. So that means VO of t will pretty much be the impedance times the current passing through the load. So it'll just be JWL R of 2 all over JWL plus R2 times I. Okay, so that's pretty much done. For VI of t, let's times JWL plus R2 with this. So it'll just be JWL R1 plus hold on, JWL. Then actually wait, hold on, let me try this again. Sorry, I'm getting a little confused right now. JWL R1 plus R1 R2. I think that's how we're supposed to do it. And then all over JWL plus R2. So now you can just pretty much combine these two. So our transfer function VO of t will all over VI of t will be JWL R2 all over JWL plus R2 times I all over. So we pretty much, since the bottom has like terms, we can combine these two. So this will be JWL R2 plus JWL R1 plus R1 R2 all over JWL plus R2 times I. These two cancel each other out. This and this cancels each other out. So now pretty much what we're left with is JWL R2 all over I think we can take the JWL out and just do R2 plus R1 plus R1 R2. Okay, that looks good. Now, what we're going to do next is factor out R1, R2, and yeah, so let's factor out that. So this is what I mean. So we're going to do R2 plus R1 and JWL plus R1, R2 all over R2 plus R1. Okay? Also, let's take out an L as well. So so we'll have to add an L down here as well. That way these two L's can cancel each other out. Sorry, it kind of looks a little messy, but let's tidy it up now. So JW R2 all over R2 plus R1 times JW plus R1 R2 all over L R2 plus R1. And we'll rewrite this as the following. There we go. And this will be your transfer function. Now, before we find out the band type of this circuit, let's get the magnitude first. So obviously this is going to be a constant, so we can just keep this to the side and just focus on this portion. So the magnitude of JW, it'll just be W. Yeah, just W. And then this one, it'll be this squared plus this squared all to the square root. So, and the reason this is just the magnitude of this is W because it'll be W squared plus 1 all to the square root, which is just W. So it'll be W and then the square root of W squared plus R1 R2 plus L R2 plus R1 squared. And what I can factor this W2, so it'll be hold on. So right now I'm trying to get this and this to cancel each other out. So let's see how I can do it. Okay, so I can do the following, and then I think I have to include a W here. Yeah. Yeah, sounds good. Okay. So pretty much if I do it like this, I can bring this into here, and then if I can bring this into here as well, and that would cancel each other out. So I can just leave like this. Oh, sorry, this should be W squared, W squared. There we go. Okay? Because that way, if I were to draw it like this would go into here, and it'll be W2. And then this would go into here and cancel that out. But then I can break the square root up into 2 as well. This and this cancels out, and then this and this cancels out. Okay, my apologies if I wasn't able to explain this properly. But now we can just rewrite this like the following. The top will just be 1 now, and it'll be R2 all over R2 plus R1. Okay, now we have to find out the band type of this. So let's take the limit for W as we approach 0. So when we approach 0, 1 over W squared, that pretty much turns into infinity. So it'll be 1 plus infinity, which will be 1 over infinity, which will make this whole thing to be 0. So this will pretty much just be equal to 0. And instead, if we were to go to infinity instead, this would go to infinity. So it'll be 1 over infinity, which is 0. So it'll be square root of 1 plus 0. So this portion will just be 1. So this will be equal to R2 plus all over R2 plus R1. So now drawing the Boyd plot graph. When W is 0, we're currently at 0. As we approach infinity, we go to 1 times R2 all over R2 plus R1. Okay? So if we pretty much increase something like this, where we have a saturation point of R2 over R2 plus R1. And then the cutoff frequency will be 1 over the square root of 2 times R2 all over R2 plus R1. And that's the next part we have to find. We have to find this cutoff frequency. So pretty much this is a high pass circuit. Or high pass filter. Okay? And now we need to find the cutoff frequency, WC. So what we do is we have HW be equal to this, and now we just have to find W in here. So let's see what we can do. So we know HW is equal to R2 all over R2 plus R1 times 1 over the square root of 1 plus 1W squared times R1 R2 all over L R1 plus R2 plus R1 squared, and HW is 1 over the square root of 2 R2 over R2 plus R1. This and this cancels out, so we just have 1 over the square root of 2 equals 1 over the square root of 1 plus 1W squared times R1 R2 L R2 plus R1 squared. So what we'll do is square both sides by 2. That way the square roots here cancel out. So we'll just have 1 over 2 equals 1 all over 1 plus 1 over W squared R1 R2 all over L R2 plus R1 squared. Okay, what should this be equal to? So let's see what R1 and R2 were. R1 was 100 ohms, and R1 is equal to R2. Okay, so R1 is equal to 100 ohms, R2 is equal to 100 ohms, and we need to know the inductance. The inductance is equal to 2 millihenries, so 0.002 henries. So we just plug these in. So it'll be 100 times 100 all over 0.002 times 100 plus 100 squared. And this should be the 100 squared all over the 100 squared, that's just 10,000. So now 100 plus 100, that's 200 times 0.002, that's 0.4. And that should give you 625 million. All right. So let's bring this to this side and let's bring this to this side. So 1 plus 1 over W squared times 625 million equals 2. Bring this one to the other side. So it'll be 1 over W squared, 625 million equals 1. Bring the W2 to the other side. All right. So W equals 25,000, and that's your cutoff frequency. 25,000 radians per second.